In the last class, we discussed some basic laws that correlate electric and magnetic fields. We discussed in particular three laws. The first two are the Gauss's laws for electric and magnetic fields respectively. We saw that the nature of Gauss law for electric and magnetic field are very similar. And the third law that we saw was Faraday's law of electromagnetic induction. So today we shall see the fourth law. The fourth law in this series, the fourth and final. So that law is called Ampere's circuital law. And this Ampere's circuital law is analogous to Faraday's law. Just like how Gauss law for electric and magnetic field was analogous to each other, Ampere's circuital law is analogous to Faraday's law. So what was Faraday's law? Faraday's law had stated that the net electromotive force, in a closed loop equals the rate of change of magnetic flux enclosed by the loop. So Ampere's law states that the total magnetomotive force through a closed loop is nothing but the current along the loop. So if you notice, even the wordings are analogous. In case of Faraday's law, the word used was electromotive force. In case of Ampere's law, the word used is magnetomotive force. So if I have a conductor which is of the structure of a closed loop, then it is something of this kind. Suppose I have this conductor which looks something of this kind. Or a wire that is bent in the shape of a square or a rectangle. So let us say that there is some current which is flowing. Then because of this current, there will be some magnetic field which is generated. Some magnetic field, let's say H, will be generated, and let us say it will have some nature when it's passing through the area that is enclosed by this closed loop. So the magnetomotive force, or MMF, just like how the electromotive force or potential is nothing but the electric field, or rather the kind of work done by the electric field along the length of the conductor, MMF is nothing but the work done by the magnetic field along the length. So this is defined as a contour integral where dl indicates the small length differential for the conductor or the loop. So if the current flowing through this is I, then it says the magnetomotive force is nothing but the current along the loop, which is nothing but I. So this happens because of the individual field lines due to the different sides of the closed loop. Now if the current flowing is I can represent this using current density as nothing but the area integral over the cross-sectional surface through which the I is flowing. That is nothing but J dot dA. So one result we get is this. So now you can see again, similar to what we saw for Faraday's law, we are correlating a single length integral with an area integral. So therefore I can use the Stokes theorem. I can convert this into an area integral by using the curl. And this should be equal to this integral. So what it means is, if I can just correlate these two. So the curl of the magnetic field is nothing but the current density. So this is called the integral form, and this is called the differential form of Ampere's law. So if you notice, for the two Gauss law for electric and magnetic field, and also the Faraday's law, we have expressed the law in two forms. One is integral form, one is differential form. And just like how Gauss law for electric field and magnetic field are very similar and analogous to each other, Ampere's law is analogous and similar to Faraday's law. So now let us write this down. Let's write the differential form of all the laws. The first was Gauss's law for electric field. That was del dot D is equal to the charge density rho. Second, Gauss law for magnetic flux. So this was del dot B is equal to 0, which is nothing but the magnetic charge density enclosed by the Gaussian surface. The third is del dot E is nothing but minus del B by del T. And fourth, del cross H is nothing but J. So just like how D and B are analogous to each other, we have correlated them using the Gauss laws, and just like how E and H are analogous to each other, we have correlated them using the Faraday's law and the Ampere's law respectively. So these were the forms which were derived by Maxwell. James Clerk Maxwell, the British physicist. So all was going good. The only thing was that Maxwell faced a problem. Maxwell was convinced with three equations out of this 4, but one equation he knew was not correct, and that was the Ampere's law. Maxwell identified a problem while working with the Ampere's circuital law. Now let us see what the problem was. Now in general, let us say that there is a closed surface which encloses some charge having charge density rho. Now suppose these charges now start moving and these charges start leaving this surface by means of current. So if now these charges start moving, they will constitute a current. Let us say that current density is some J. Then the net current outward current through the surface I. The net current, I can write it as nothing but the charge density multiplied over the area. So therefore, this is nothing but the area integral of the J vector with the area differential, where on the surface this is the A. Now this is the current that is flowing out of the surface. So what Maxwell saw was, or rather what Maxwell knew, that behind everything, whether it's current or energy, the law of conservation still holds. That means if there is some current that is created by charges leaving the surface, then definitely that is caused by the charges which are enclosed by the surface. The cause of this current is nothing but the charges that are being enclosed by the surface. So he said that if there is some current, that means the charges inside the surface must reduce. As simple as that. If charges are coming out of the surface, accordingly the number of charges which are causing the current must also reduce. So therefore he said that this should be nothing but the rate of change of, or rate of reduction of charge. So therefore he said this is nothing but del Q by del T with a minus sign, which indicates that since charges are leaving the surface, the charges enclosed by the surface must reduce. Hence you have this minus sign. So I can represent the Q using the volume charge density rho in this form. So now again I am correlating an area integral with a volume integral. So therefore we can use the divergence theorem and say that the divergence of the current density vector should be equal to the rate of decrease in charge density. So let's rewrite what we saw. So that means, correlating this with the divergence theorem, I can say that the divergence of the current density is equal to this quantity. So therefore, this two should be equal. That means del dot j bar is nothing but minus d rho by dt. This equation is called the equation of continuity, because it comes as a consequence of the law of conservation of matter. That's what we said, right? The current happens due to the charges. So therefore, if there is a current, the charges from the source must decrease. So he said, so Maxwell essentially derived this. He said that whenever there is a current, this must hold true. The equation of continuity must hold true. So far it's okay. But Maxwell found that Ampere's law in the present form did not obey this continuity equation. The Ampere's law in the present form, what he saw, or what was proposed by Ampere, and that's what he also worked with, he saw that no, Ampere's law is inconsistent with the equation of continuity. How? So remember what we derived. Ampere's law was this. So now, if you take the divergence on both sides, you will get this. Now, what do we know? If you look at the left hand side, you will see that we are trying to take the divergence of a curl. And as we know, the curl indicates rotation. So the divergence of a curl essentially is trying to tell you how much of the curl vector is diverging from a point. And by the nature of the curl, we can prove it intuitively. You can also mathematically prove that the divergence of a curl is always zero. So what we are seeing is the divergence of a curl is zero. So therefore the divergence of the current density, the conduction current density vector, is also zero. So if this is zero, but we just said that the divergence of the current density vector cannot be zero. It is minus d rho by dt. So clearly there is some kind of a anomaly. Ampere's law in the present form says that the divergence of J must be zero, but the equation of continuity says that the divergence of J must be this quantity, which is non-zero. So Maxwell said, okay, since this equation of continuity depends on the law of conservation of charge or matter, this has to be correct. So he said, no, this cannot be true. So therefore he said del dot J cannot be zero. So Maxwell proved that this was incorrect. So So then he said that as per the equation of continuity, del dot J should be nothing but minus d rho by dt. So if I take this on the left hand side, I will get this is 0. So now this can be made equal to the divergence of the curl of the magnetic field. So I can say the divergence of the curl of the magnetic field intensity is nothing but so this has to be 0, and we have just proved that as per the equation of continuity, the right hand side term is also 0. Now as per Gauss law, I can write rho as nothing but the divergence of the electric displacement density. We proved this in the last class. So therefore I can say this is del dot J plus the time derivative of del dot D. So this is nothing but, since the divergence operation and the time differential are independent operations, I can say that the divergence of this entire vector sum will be equal to the left hand side. So therefore, removing the divergence, I can say del cross H is equal to J plus del D by del T. This is the modified differential form of Ampere's law. This was the biggest contribution by Maxwell. So if I write the integral form, I can write that H dot dl in a closed path is equal to the area integral of this entire quantity. This is the modified integral form of Ampere's law. So one of the biggest contributions by Maxwell was to correct Ampere's law and make it consistent with the law of conservation of charge or the law of conservation of matter. And this proved to be a path-breaking development. Why? Because when Ampere proposed his original law, he used a current carrying conductor as the basis. That is why you have this J term. So now if I look at this, the J term, as you know, is called conduction current density. So originally, when Ampere proposed his law, the second term was not there. But there are many examples in real life where even without having J, you can have a magnetic field. That means you can have a magnetic field without having a physical conductor which is carrying current. So that happens because of the second quantity, which is called as the displacement current density. So now I just mentioned a minute or two back that if J becomes equal to 0, that is, we do not have a conductor and yet we are able to have a magnetic field. As per Ampere's original theory, that was incorrect. Because the moment J becomes 0, the whole right hand term would become 0 and then there would be no magnetic field. When electromagnetic waves are propagating in air, we discussed that the best and most evident example of propagation of electromagnetic fields is when you make a call using your mobile phone. Now once the wave starts traveling, it is seeing only air, and we mentioned that the wave which is traveling in air has electric and magnetic field components. How is it able to have a magnetic field without any conductor? How is it able to sustain those fields? That is explained by the displacement current density. Now this is something which is very, very important. This second and more conventional application of the displacement current density is to explain how the current flows in a capacitor. When you have a capacitor, you essentially have two plates which are separated by a dielectric. But yet we say that even though there is no physical connection between these two conductors or these two conductive plates, there is some non-zero current which is able to flow. How is that possible? Why that happens is because in your basic electronics course or electrical course, you must have learned that the current can only exist in a capacitor if it is alternating or time varying in nature. That is where that C dV by dt comes in. Now what happens is if you have time varying currents, there is charge accumulation in the two plates. There is unequal charge accumulation as a function of time on these two plates. So therefore, because of unequal charges, there is an electric field which is created. A time varying electric field or electric displacement which is created, either D or E, whichever you want to say. So when this is created, the displacement current comes into picture because this matter is dielectric. It is an insulator. J has to be 0 in this medium. So if J is 0, this is non-zero, which makes the current flow in the capacitor. So therefore, due to the current, there is some non-zero magnetic field due to the current element, but the current which is actually flowing in the dielectric is not due to any charge carrier, but it is due to changing of the fields at either end, which gives rise to something called as displacement current density. So this is something which is very, very important. So this answers many questions. The second question it answers is current through capacitor. So this is due to displacement, current, density. So this was one of the most important contributions by James Clerk Maxwell. He not only correlated the electric and magnetic field quantities by some equations, he also made a modification in Ampere's law which accounted for a very important anomaly. And that is why Maxwell's work was regarded as one of the most path-breaking works there ever was. So therefore, let us write down all these 4 laws, which are also called as Maxwell's equations. So let's make a column. The law, integral form, and differential form. So first is Gauss's law for electric displacement. So the integral form for that is and the differential form is nothing but using the divergence. The next is Gauss's law for magnetic flux, and that is nothing, simply replace D with B, that is equal to the net magnetic charge, which is always 0, and here also the divergence would be equal to 0. Then comes Faraday's law, and the integral form for that is E dot dl in a closed contour, that is nothing but so the differential form of that would be the curl of the electric field is nothing but minus del B by del T. And finally, Ampere's law modified. This is nothing but just replace E with H dot dl, that is nothing but the integral of conduction and displacement current sum, and the differential form is del cross H is J plus del B by del T, and these 4 equations in their respective forms are called Maxwell's equations. Now looking at integral form and differential form, you can easily say that the differential form looks much simpler, and of course it is also. It is much more easier to do. Now the integral form are general solutions, and the differential forms should be used only when the medium where you are applying this is continuous. Why? Because if there is some discontinuity, the derivatives don't have any manner through which you can define that discontinuity if I am going from medium 1 to medium 2. But by carefully changing the limits in the integral forms of these equations, you can use these integral forms in non-continuous media also. So most of the time when we are not dealing with medium being discontinuous, we can definitely apply the differential forms. So now let us slowly make a transition from continuous medium to media which may not be continuous, or to state this in a little bit more of a different manner, if there are two media which are separated by a boundary. Now before we observe what happens at the boundary of two medium, let us define some quantities. Let us define something called as surface charge and surface current. Now, suppose we have a medium where there are some charges. Let us say those charges can also flow. So let's say that medium has some charge density rho and some conduction current density J. Now don't just say current density, because after looking at what Maxwell did, the term current density is very vague. You must mention whether it is conduction current or displacement current. So let's mention conduction current density J. So this is nothing but coulomb per meter cube, the volume charge density, and the conduction current density is ampere per meter square. Now suppose I have this medium where the charges are there, they are also moving with some current density, conduction current density J. Now let us say I am defining a boundary. I am defining a boundary. Now it is very interesting to see, or rather redefine, the charge density and current density when we are very close to the boundaries. So now at the boundary the medium is ending. So therefore, if I am looking from the boundary into the medium, let me define a distance called d, small d, distance or depth into the medium. So now if some charges are existing here also, I can now say that the surface charge density is nothing but the density of the charges near the boundary as d becomes very, very small. So I can define surface charge density. Let's call this as rho s. So if the volume charge density is rho, and I want to say that, or rather I want to express the charge density over area, that means I want for surface. So that is like saying, since this is a volume charge density, it is over 3 dimensions. If I want to make a surface and I am looking at the medium boundary this way, no matter whatever I do, I will always encounter a volume element, and this is my dV, this cubical shape. So the surface charge density at the boundary can be defined by defining the surface properly, by putting the limit that the depth of this medium d should tend to 0. So to convert volume charge density into surface charge density, all I need to do is multiply the rho with the d and put the condition limiting d tends to 0. So it is like saying how many charges are there in one line just inside the boundary of the medium. This is called as surface charge density, and the unit is coulomb per meter square, because I am talking about density of charges on a surface. So therefore obviously it has to be the function per unit area. So likewise I can define surface current density, which I will define as Js that is nothing but, again, limiting d tends to 0, the conduction current density multiplied by the depth, that is JD, and the unit of this now will be ampere per meter. So d tending to 0 gives us the surface charge, and because of that we have something called a surface current also. So we have just defined these two quantities, surface charge and surface current, using some approximations where we are defining some small depth d inside the medium, and by making d tending to 0 I am sort of looking at the immediate area vicinity inside the medium. So we have defined these quantities and we are going to use them for our analysis. So now, having established the 4 Maxwell's equations and the concept of surface charge and surface current, let us now see how the fields, that is to say electric and magnetic fields, they change at media boundaries. So now let us say this is a border between medium 1 and medium 2. So just like how we defined a small depth d into either media, let us do the same thing over here. On either side, let us consider only small depth. Let us draw a rectangular section where we are interested to see how the fields are changing. Now, before we do that, let us define the normal vector. Now, let us say we have some fields over in medium 1 and we would like to see when the fields come at the boundary of medium 1, how they get transformed into medium 2. So therefore, it is like saying medium 1 is the one where we are sitting right now, or where our fields are sitting right now. Let us now see what will be the effect in medium 2. So medium 2 is the new territory. So therefore, let us define the unit normal in this direction. So let us first talk of electric fields. So electric field can exist in any direction, but irrespective of which direction the field is, I can always break it down into vertical component and horizontal component. Why? Because why only these two components? In spite of the fact that you know electric field, by now you know that electric field is a 3D quantity. It can have components in x, y and z directions only. I can in fact tell you that we don't need to look at the third axis at all. That's because we are now very interested to see what is happening at the boundary. So at the boundary, I can define, let us say the electric field in this medium is E1 and the effective electric field becomes E2. I can define a tangential component of the electric field along this axis. Let us say the tangential component in medium 1 is ET1 and the normal component, which is directly incident on the boundary, is En1. So even though we are denoting the electric field in two components, we can also have a third component which is either coming out of the paper or going in. But there is no point in defining that, because it is, if it is coming out or going in, it is parallel to the medium. So therefore, it will behave the exact same way as the tangential field. So no need to define the third component. So let's write this down. ET1, the tangential component of E1, and En1 is the normal component of E1. Likewise, when E1 becomes E2 in medium 2, let's call this ET2 and let us, for the sake of continuity, maintain the direction and call this as En2. Now, let the width of this rectangle be some W and the length from here to here be some L. So now what I can do, firstly, I can look at the electric field and integrate it over this closed ring or closed loop, this dashed boundary, as a function of length. So therefore what I can do, I can apply Faraday's law. When I apply Faraday's law, essentially what I am doing is I am multiplying the electric field with the length, because remember there was the E dot dl integral. So right now, since we have discontinuity, we cannot apply differential forms of the laws. We have to apply the integral forms, which are more general. So therefore, what I can do is I can look at each side of the rectangle and apply the electric field to find out what is the electromotive force. So the EMF, now let us say we will start from here. We will start from here and move clockwise. Let us go this way for integrating. We will start from here and come back at this point. So the EMF is nothing but, let us say from A, B, C, D. Along the path AB, what is the electric field? It is ET1. EN1 will not play any role because it is perpendicular and orthogonal. And what is the length ET1 is seeing? It is seeing L. So over AB, it will be ET1 times L from A to B. Now let's go from B to C. Now B to C, we are moving this way. So what will happen is EN1 will come. So ET is orthogonal to this path. So the dot product will be 0. So it will not play any role. So therefore, from B to C, it is EN1 times half the width in medium 1 plus EN2 times half the width. This entire for B to C. Then from C to D, you see that the direction of integration and the direction of the field are opposite. So it will be the dot product with a negative sign. So ET2 times L with a minus sign. Now again from D to A, so this will be from C to D. From D to A, it will be very similar to B to C except with a minus sign. So this will be minus En1 W by 2 minus En2 W by 2. So let us write this a little more properly. That is nothing but now, as per Faraday's law, the net electromotive force around this loop must be nothing but the rate of change of total magnetic flux inside this area. So therefore, this will be equal to minus dB by dt times the area, which is L times W. So what is B? We have not defined B. B is the magnetic flux density which will be perpendicular to the area. So that is either going in or coming out. It could be any one of those, we are not really concerned. What may happen is in medium 1, B may be equal to B1 and medium 2, B may be equal to B2. But right now we are not very much bothered. We can define it definitely as some function of B1 and B2. But what is more important to know is that over here, if I now put the limit W tending to 0, why? Because I want to make the width of this rectangle very small. I am interested only near the media or the surface phenomena. The boundary between two media is acting like a surface. So therefore, to observe the phenomena at the boundary, I can put the limit W tends to 0. So the moment I put that, this term will get cancelled, this term will get cancelled. And even over here, the area will tend to 0. So even over there, this is going to get cancelled. So the right hand side will become 0. Only what I have is ET1 minus ET2 equals 0. That means this is the result. So what this proves is that the tangential component of the electric field in general is continuous across boundaries. Okay. The tangential component of the electric field is always continuous across boundaries. So what we are proving? We saw ET1 and ET2 are equal. So the tangential component on this side just at the boundary and tangential component on this side just at the boundary are continuous. They are equal. This is something very interesting. So the electric field tangential components coexist as if there is no boundary. Now it is time to look at the normal components. So now let us look at the normal components En1 and En2. So let us look at medium 1, medium 2. So now let us change the definition slightly. Rather than defining En1 and En2, I will define the displacement density dN1 and dN2. Why? Because if you assume that the two media are isotropic, then dN1 is epsilon 1 times En1 and dN2 is epsilon 2 times En2. So therefore there is almost a kind of linear relationship between the two. And the other reason why I am going for D rather than E is because it will be easier to apply Gauss law. So let us say this normal is incident on some surface at the boundary. This dN1 is incident on some surface and dN2 is coming out of the other side of the surface. Let this distance be d and the cross-sectional area be A. So in that case, if I apply the Gauss law through this closed surface, what will I see? If I define the normal on this surface this way and the normal on this surface this way. So in that case you will see the net electric displacement on either side will have a minus sign difference. So therefore I can say that the net displacement that is nothing but, if you remember, it is integral of the d with the area differential. So this is nothing but dn1 times a minus dn2 times a. You can also write it as minus d1a plus d2a. It's one and the same. So what does Gauss's law state? It states that the net electric displacement is nothing but the enclosed charge. So what is the enclosed charge? The enclosed charge is a function of the charge density both at the volume and at the surface. So the charge density will be nothing but volume charge plus surface charge. Now be very careful, we are applying the funda of surface charge. So volume charge we can define as the, let us say the charge density is rho. The volume is nothing but A times D. So the volume charge will be rho A D plus the surface charge, that is rho S. And since surface charge is per unit area, we will multiply with A only. So what we get essentially is this. So now we will put the surface condition where limit d tends to 0, because we want the surface to be just on either side of the boundary. So if I put this limit d equal to 0, this term will cancel out. So then I will put, or then I will get dn1a minus dn2a is rho s a. So I can cancel out these a terms, and dn1 minus dn2 is equal to rho s. So what we can see, the normal component of the displacement, the electric displacement, they differ by the surface charge density between the two medium. So you may argue that what if the surface charge density at the two medium is different? No, because we are defining medium at the boundary. We are putting the limit d tends to 0. So therefore we are converging onto essentially one set of points where the charge density will be the same across this line. So therefore it is essentially the charge distribution at the medium. So if I want to write this in the form of electric field, I can write this as epsilon 1 times En1 minus epsilon 2 times En2 is equal to rho s. So whichever one you want, you can write. Now let us look at this rho s a little bit more. Under what condition will rho s exist? Rho s will exist only when either of the two medium is a conductor, because charges in practice can only exist inside a conductor. So, for good dielectrics or insulators, rho s will tend to 0, because as you know, in insulators there is no concept of free charges, so to speak. So for good dielectrics, dn1 minus dn2 will be equal to 0. So that means dn1 is equal to dn2. Now, what would happen? What would happen if either medium 1 or medium 2 is a metal or a conductor? In that case, I can definitely say that some rho s will be there. Very good. But is that the complete problem? So I say suppose medium 1 is dielectric and M2 is a conductor. How would this relationship change? How would this relationship change? What can we say about the electric field inside a conductor? The electric field inside the conductor will become 0. So therefore, whatever is the surface charge density, that itself will be dn1. So this is how the condition for displacement changes with different media. Now, we applied two laws so far. One was the Faraday's law, the other was Gauss's law for electric field, and we found out what happens to the normal and tangential components for electric field or electric displacement. So we now need to see what happens for the normal and tangential components of the boundary, or of the magnetic field, at the boundary. So therefore, let us see that. Suppose we again have a medium boundary. Suppose I have some normal component of the magnetic flux density Bn1 and Bn2. If I apply Gauss law for magnetic field onto Bn1 and Bn2, I don't even need to do anything. Just by looking at the analysis for the electric field, I will get Bn1 minus Bn2, that is equal to the magnetic charge density, which is always 0. So without even having to solve some big proof, I can say Bn1 minus Bn2 is equal to 0, since Gauss law for magnetic flux. So with this I can say Bn1 is equal to Bn2. So the normal component of the magnetic field or magnetic flux, whatever you may want to say, will always be continuous. So even when the field is traveling, or the field line is traveling from one medium to another medium, the normal component is not changing, just like how the tangential component for electric field is not changing. So now let us look at the tangential component of magnetic field. So therefore, again let us define a small rectangle. Width is W, length is L, and let the tangential magnetic component over here be HT1 and this be HT2, and the normal component be HN1 and this is HN2. So again, if I now apply the Ampere's law, if I apply the Ampere's law by integrating the magnetic field around this closed path, what I will get? So the magnetomotive force is nothing but, let us mark the direction of integration, which is clockwise. So it will be from A to B plus B to C plus C to D plus D to A. So let's write those down. A to B, the integral is HT1 times L. B to C will be what? Just like the case of electric field. Now for HT2 there will be a minus sign. That is, we forgot D to A. D to A is nothing but, oops, I made a mistake. It should be HN1 over here, because it's the normal, minus HN1 plus HN2 W by 2. And that will be equal to what? The net conduction current and the displacement current. So now observe what I am doing. Remember, the right hand side for Ampere's law was J plus del D by del T. So now I have to write the current as a function of surface current as well as the whole volume current. So I can say, let the conduction current be J. It will be J times area. The surface area is what? L cross W. Plus del D by del T, L cross W. Plus I will have the surface current density Js, which is nothing but J times W. Or Js is J times W, but since we are now looking at the current along the surface, or the surface current, which is a function of, or which is the product of surface current density multiplied by the length, so which is Js times L. Because we are looking at, this is the surface current, which is surface current density times length. Now surface current cannot exist this way. It will only exist along the surface, either on top or the bottom. So again, if I apply limit W tends to 0, this will vanish, this will vanish, this will vanish, this will vanish. So what I will have left behind is, I can cancel out the L components also, HT1 minus HT2 is equal to Js. So just like how the normal component of the electric displacement across the two media was different or was differing by the charge density, the normal component of the tangential component of the two magnetic fields across the media differ by the surface current. So I can say for good dielectric, there cannot be any charge or any current inside a dielectric. So I can say J is equal to 0. In that case, the two will be continuous. So now the general condition result for the tangential component of the magnetic field, what we saw is this. But it is actually not proper for us to write it this way, because both left hand side and right hand side are vectors. Both left hand side and right hand side are vectors. So therefore, we must write this in the vector form. So in general, since the displacement current has gone in the boundary, as per Ampere's law, this is what we know. So what I can say is that the direction of H and J would essentially be perpendicular to each other. So let us see what this means. This is medium 1, medium 2. Over here at the boundary I have HT1, over here I have HT2. Let us define the normal over here. So since we are taking the curl, we are essentially doing a cross product of the normal or some normal vector, because it's the directional derivative, and the HT1. So what I can write essentially in the vector form, this essentially becomes something of this kind. So now if I apply the right hand thumb rule and take the cross product of this N and HT, so my curling fingers are pointing from N to H, so my thumb is pointing down. So therefore at the surface current will exist going into the plane of the paper. That is how it is. So what we are seeing is, if you have two different tangential components of the magnetic field at the two boundaries, in general a surface current will be created which is perpendicular to the plane of the paper. So So now with this, let us summarize what we have done so far. Let us summarize, right, what we call as the boundary conditions. So what we proved, that the tangential components of the electric field are continuous. The normal components of the displacement is equal to the surface charge. In case of the normal component of the magnetic flux, they are also continuous, and the tangential components of the magnetic fields are correlated using surface current. Now these are the general conditions. What if the two media are dielectric and dielectric, that is insulator? So this condition will not change because it's independent of medium. This one will be Bn1 equals Bn2. Now we proved already that in dielectric there is no concept of surface current. So dN1 will be equal to dN2. And also in case of dielectric there is no concept of surface current. So therefore we can say HT1 will be equal to HT2. So dielectric boundaries are the best. All components, normal and tangential, are continuous. So that is why dielectric components or boundaries are easy to analyze. Now what if I have dielectric with a conductor? Say medium 1 is dielectric and medium 2 is conductor. Now what will happen? I can say that the electric field will still be continuous. But we have already proved that the electric field inside a conductor is zero. The moment you enter the conductor, the electric field becomes zero. We have proved this. So we can say that ET1 is zero. So at the boundary, something will happen which will make the net electric field at the boundary zero. What about D? Same. If electric field inside conductor is zero, the displacement also has to be zero. So likewise, I can say dN1 is equal to 0. What about magnetic field? What about magnetic field? We have already related electric and magnetic field using the Maxwell's equations. So if electric field is 0, the magnetic field will also be 0 because both are codependent on each other. If you apply Faraday's law, this is what you will get. So I can say Bn1 is equal to 0. Now what about the tangential component? Well, HT2 will be 0, but the surface current will exist. I'm sorry, there's a small mistake. dN2 will be 0, but the surface charge will still be there. Because metals do have charge. Yes, we cannot write 0. So in case of the tangential component of magnetic field, if Bn2 is 0, then the H inside the metal will also be 0. So what we will have is this N cross HT1 will be equal to the surface current in the metal. And that's it. So these are called as the general boundary conditions. So in today's class, we looked at all four laws or the basic laws of electromagnetics, and we grouped them together as something called as Maxwell's equations. Now Maxwell's equations are not just those four laws, but also the correction in Ampere's law. And after we established the Maxwell's equations, we looked at, using those four equations, how the fields are behaving at the boundaries for different kinds of material. So we shall continue from this point on in the next class. Thank you.